The James Webb Space Telescope, or JWST, which was launched on Christmas Eve, is set to transform our understanding of the cosmos by allowing scientists to explore further backwards in history than ever before. The telescope, which was initially suggested in 1989 and had cost almost $10 billion, will be able to look into space beyond previous telescopes. It is due to its 6.5-meter light-gathering primary mirror, which is nearly 3 times larger than the Hubble Space Telescopes. As a result, we view items as they were in the past due to the apparent time it takes light to come to us. That implies viewing the 13.8 billion-year-old cosmos as it was 100 million years after the Big Bang for things that JWST will be able to scan. As a result, scientists should be able to solve the enigma of dark energy. This force causes the universe to expand at an accelerated rate with the assistance of this mighty space telescope. In addition, the JWST might be able to shed light on the structure of dark matter, a material that isn't made up of protons and neutrons like most of the objects we see daily, and doesn't respond to light in the same way that ordinary matter does. On the other hand, dark matter interacts with gravity and exerts a force that prevents galaxies from colliding as they revolve. As a result, these components of the universe are sometimes referred to together as the dark universe. Even though they are unconnected and have essentially opposing effects, dark matter pulls galaxies together. In contrast, dark energy drives the universe away. Dark matter, along with dark energy, is the most critical concern in physics since they account for up to 95% of the stuff that surrounds our universe. As a result, the release of the James Webb Space Telescope may still provide data needed to evaluate one of Stephen Hawking's most contentious theories, that dark matter, or the undetectable substance that makes up most of the matter or components in the cosmos, is made up of black holes developed in the Big Bang's early moments. 3 astronomers have proposed a hypothesis that explains the presence of dark matter and the development of the universe's most significant black holes, as per Live Science. Furthermore, they claimed that numerous new equipment, notably the James Webb Space Telescope, which was deployed, might finally provide the data needed to examine Hawking's renowned theory. According to astronomers, black holes arise only after massive stars die and cause the collapse of their gravity. Therefore, creating black holes necessitates many stars, which requires a large amount of ordinary stuff. From computations of the early cosmos, scientists now know how much standard stuff there is in the universe. They think, however, that there isn't enough ordinary matter to produce all of the dark matter, which relates to more than 80% of all staff in the universe. As a result, Stephen Hawking theorized in 1971 that black holes emerged in the chaotic environment of the Big Bang's early moments. He described how pockets of matter may achieve the densities required to form black holes on their own, overwhelming the universe with them long before the first stars sparkled. He further speculated that these primordial black holes might just be the source of dark matter. The JWST should offer a better understanding of the universe's growth by enabling scientists to view Type 1 supernovas deeper into the universe, and hence further backward in history than ever before. The light emissions of this type of supernova, which occurs when a carbon-oxygen-rich white dwarf together in a binary system explodes as a result of its eagerly sucking material from its partner star, are so consistent that they are dubbed standard candles. Astronomers have been using these standard candles to estimate distances for decades because of their consistency. However, examinations of distant instances in the late 1990s revealed something startling about the universe. Albert Einstein was stunned when astronomer Edwin Hubble discovered that the universe was expanding in the early 20th century. Like the rest of science, the brilliant physicist had assumed that the cosmos was fixed and unchanging. He even included a cosmological constant in his revolutionary equations of general relativity to avoid them from forecasting a dynamic and evolving universe. This finding rocked physicists, although not as much as the discovery in the late 1990s that the cosmos was not only expanding, but doing so at a faster rate. For example, astronomers determined in 1998 that the more distant a type lost supernova was, the stronger the impact of redshift, the lengthening of the wavelength of light toward the red end of the visible spectrum drifts away from an observer. This informed astronomers that the farther things like supernovae or galaxies are from us, the faster they recede, implying that the universe's expansion is speeding up. However, it is yet unknown and unclear what is causing this acceleration. The term dark energy has been coined by scientists. Dark energy is a quiet, seamless, and uniform component responsible for no less than 70% of the entire amount of matter energy in the cosmos, according to Luz Angela Garcia, a cosmologist at the University of ECCI in Colombia. They employ dark energy to explain the large-scale origins of the universe observable by wide-area astronomical surveys and to offer an explanation for the observed expansion rate today. Garcia is now investigating hypothetical early dark energy models, or EDEs, that suggest this force existed earlier. In their most recent study, Nada Haran from Nico Cappelletti of the University of Miami, along with Gunther Hasinger from the European Space Agency, investigated the hypothesis of primordial black holes, examining how they can explain dark matter and perhaps answer other cosmological issues. By looking for the first stars, cosmos, and supermassive black holes, they discovered that primordial black holes might play a significant role in the cosmos. However, they also stated that their findings suggest that stars, galaxies, and SMBHs arise very swiftly in cosmic history, maybe too quickly to explain the current universe's creation and expansion processes. While this is merely a concept, experts believe it might be tested shortly. According to them, the James Webb Space Telescope was created precisely to address concerns regarding the origins of galaxies and stars. Furthermore, the next generation of gravitational wave detectors, notably the Laser Interferometer Space Antenna, or LISA, is expected to disclose more about black holes, even primordial ones, if they exist. The two observatories, according to astronomers, should provide enough data to piece together the narrative of the earliest stars, and perhaps the beginnings of dark matter. Examining early and distant objects might help with more than simply the quest for dark energy. It might also aid in a better understanding of dark matter's nature. The predominant kind of mass in the universe is dark matter. They know it isn't made up of the neutrons, protons, and electrons found in everyday stuff. Instead, non-luminous matter might be a better term for dark matter, which makes up around 25% of cosmic density and therefore does not generate or absorb light. It's been tough to figure out what dark matter is, since they can only detect it implicitly through its gravity. Using the JWST, studying the evolution of early galaxies might assist astrophysicists, astronomers, and cosmologists in fully understanding the role of dark energy in these processes and restricting models of this mysterious element. In addition, the JWST will be beneficial in examining early galaxies' black halos. Enigmatic shells encircle most galaxies. Observing the abundance of these galaxies might aid in determining which set of theories is correct, putting researchers on a road that may lead to a solution to the dark matter puzzle. Because such early galaxies originate in the earliest dark matter light sources, JWST will vary some hypotheses about the nature of dark matter by elucidating the nature of these earlier than usual gravitationally bound masses of dark matter. We hope you find our narration delectable. So offer a like and hit the subscribe button before you leave.